Okay, good morning, everyone. Welcome to class. Can you hear me? Is my voice clear? Okay. All right. Thank you. Just give me 1 second to plug in my second mic, so you guys can actually hear me. I think. Just give me 1 second. I would want to plug in the second mic. Okay. Okay. I just changed my mic. Just wanted to ask, is the voice better? Can you still hear me? All right, guys. Thank you. Okay, so welcome to lab. Um, so in this lab, what we're going to do is to go through the code that is related to the lecture that I gave yesterday. So if you actually look at the slides, let me quickly share them here. So these slides basically are made from the book and kind of cover some of the basic concepts of async IO. Now, if you actually go through the slides, you'll actually see that we kind of mentioned some examples here. Um, and so these examples are what we're going to go through. So you know, uh, we'll go through these examples 1, 2, 3, 4, and 5, which are all from the book. And so I'll share the code with you as well, so you can play around with it yourself, and then maybe submit a task related to these examples. Um, so let's just get started with that. So we're going to start off with the first example now. We're kind of starting off with something similar to what we did in class at the start of the week. And we're basically starting off with a sequential task. So what we have here is, if you kind of look down here from line 26 onwards, um, all we're doing in this program is we're basically calling this countdown function, just giving it two arguments. The first argument is basically the name of the function, or the task rather, and then we're kind of giving it a second argument basically, which is the delay. Um, so now if you, so we're calling this function 3 times. So you see countdown is called 1. First time it's called, we call it, we give it the name A. Second time we call it, we give it name B. And then third time we call it, we give it name C. And then the delay for the first one is 1 second, and then it's 0.8 seconds, and then 0.5 seconds. And then if you go into the function, all the function does is it basically prints the name um, and just does some sort of indentation, and then it kind of prints the tab. So you get a nice looking output. And then so this is just the number of indents that this will do. So just kind of indenting the output of this function. And when you actually see the output, this will kind of be clear. And then you have a number, n is equal to 3. And what you do is you basically loop 3 times. And all you're doing in the loop, every time you loop, is you first sleep. So your function sleeps for time which is equal to the delay that you've passed in. So for the first time that we call countdown, we basically will sleep for 1 second. Then we're just going to print or calculate the duration. So when the time from when the function started or when we started running the program. So this start basically is the time when the program starts running. And then what we do is we basically just, every time we basically loop in all tasks, we're just going to print the duration. And then finally, we're just going to print the duration, and then we're going to decrement the loop. So this means is we start with n is equal to 3, then we go to n is equal to 2, and then to 1, and then after that, I guess we stop. So basically loop 3 times. And then in every iteration of the loop, all we're doing is we're just printing the time that has elapsed since the start of the program, and then we just print we just indent or add some spacing, and then we just print the name of the task, and then we print the value of n. So this is a sequential program right now, so there's no async IO here. So all you basically do is you just call the countdown function 3 times. Um, every time you kind of give a different delay. And in every call, what will happen is that your function um, will display the value of n. So it'll just start from 3 to 1. So print that, it will print its own name. And before doing that, every time it will sleep for an amount equal to the delay. So the first one, because you're giving it a delay of 1 second, so it basically loops 3 times. That means that it's going to sleep for 1 second every time. So by the time the first um, uh, function call is completed, about 3 seconds will have passed. And then for the second one, you'll have around 2.4 seconds for that one to complete. And then the third one should take about 1.5 seconds to complete. But they will be completed one after the other. So you have the first one, then the second one, and then you have the third one. Okay, so let's run this, and then I'll show you the output. You can see we waited for 1 second, 2 seconds, 3 seconds. So we completed in about 7 seconds, right? Um, so this is basically a sequential program, and so the purpose of this indents was just to kind of show you that okay, the first task or task A basically is shown at this place, and then task B is kind of indented and shown at this place, and you can see that this kind of is shown together. So this is just showing that task B will start after task A, and then task C will start after task B is completed. And so all these tasks are basically run in this manner, but this is in fact sequential. In fact, if I was kind of writing this code, I might even give this guy a little bit of an indentation, because this one, the second one will basically start after the first one. But I guess uh, the author of the book didn't really do that, but that's fine. You kind of get the idea. So this is the sequential kind of task that we're doing. Now, because we're kind of getting a delay in every time we kind of call the countdown function, we could kind of think of every call as maybe a um, distinct concurrency task that we have to do. So you could think of the first task, call it, let's suppose, a database or a DB request, right? And we could think of the second task as something like, I don't know, uh, remote server request or something, right? And you could think of the third task as maybe a hard disk operating. operation or something, or a disk read. And so these are kind of concurrent tasks, right? And you don't really have to wait for one to complete before you initiate the other. So what you could do is use multi-threading or use async IO to kind of uh, run these concurrently, right? So what you can do is you can um, now with async IO, you basically what you would need to do is to convert this task or this function into a coroutine, right? Um, and then basically treat these guys as objects or as kind of calls to these coroutines, um, and then maybe also use an event loop to kind of manage these tasks, right? So if you want to kind of introduce concurrency here, the couple of things that you will have to do, right? And I hope you guys kind of remember this from the previous lectures. The first thing that you'll have to do is you'll have to kind of write async here. So the program kind of knows that you're going to, so this is an asynchronous function. Of course, another thing that you will probably need to do is to import async IO, right? So you're going to be using async IO. Um, and then you also need to kind of tell the program where it can wait, right? So this is the part where you can kind of wait, right? So you will have to write something like await here. So you have to use the await keyword. And what that kind of will tell Python is that, okay, once I get to this line, the program would be willing to, or the coroutine would be willing to kind of give up control, right? And that's what you kind of want to do here, right? So this is one change that you will have to make. Another change that you will have to make is you will need to kind of create um, an event loop, right? Um, and then that event loop basically will um, manage these tasks, right? And if you actually go to the slides, you actually see some functions. Let me bring those up here that can be used for this purpose. Um, so with this, you can kind of see that. So so you have obviously have to introduce the await and the async keyword, right? So any function that you kind of want to convert into a coroutine, you have to put the await keyword before that, and then inside that function, inside that part, which you want to, the part where you want to run asynchronously, you have to put, sorry, the part where you kind of want to um, you want the program to indicate that it can give up control here, you put the await keyword there, and then the async keyword basically indicates the function or part of the program that basically uses async IO, right? Or basically is a coroutine. So you basically convert a function into a coroutine by writing this async keyword. So that's the first thing that you'll have to do. And then one more thing that you'll have to do is obviously get um, the event loop. So async IO dot event loop. So this function basically returns the event loop for the current context. So this will basically give you a loop object, right? So what you can do is use this function to get a loop object, and then that loop object can be used to manage tasks. And right now what we're going to do is we're basically going to take this loop object to actually create tasks. This is something that we haven't done in the previous example, but it's very simple to do. So what this does is this method basically is used to uh, run coroutines concurrently as task objects. So we'll kind of call this as well, and then we may call, maybe this one, so run until complete. So this may also be used. So let's now go ahead and take a look at the concurrently or the concurrency example. So I'm going to kind of copy paste that from the book. And then I'll just highlight the changes and show you what it does. And you don't have to worry about copying the code right now. I'll share the code with you in a second. So once I actually have gone through these two examples, I'll share the code with you. Okay, so now notice as compared to the previous program. So the first thing that we did was we had to import async IO. Then we had to convert this countdown function into a coroutine. So we basically wrote down this async keyword before the countdown function. And then over here, we said await, and then we basically say async io.sleep. Now, one thing that you may have noticed is in the previous sequential program, this was time.sleep, right? And we're not really using time.sleep here. We're using async io.sleep now. This is important to note, although this is a small difference. The reason why we don't use time.sleep is because it's a blocking function. So it does not really support concurrency. So if we use this as time.sleep, what will happen is that our program will go to sleep and it will not hand over control, even though it has the await keyword in front of it. But the time.sleep function does not support concurrency. It's a blocking function. And so our program will still take the same amount of time to execute. So I'll write this as async io.sleep. This async io.sleep also is kind of like a coroutine type of a function, and this can also be used to put a coroutine or part of a program to sleep as well. So oftentimes you can kind of write async io.sleep and then give a delay of 0. And what that will do is your coroutine will go to sleep for 0 seconds. But that doesn't really mean anything. I mean, sleeping for 0 seconds, but the effect that that has practically is that it is kind of like a signal to the coroutine to kind of hand over the control to another coroutine, and we'll use that in one of the other programs that I'll talk about. So that's what we do with this async IO dot sleep. So right now we're kind of making it sleep for the delay that is being passed to each coroutine. Okay, so these were all the changes that we needed to make to the countdown function to convert it into a coroutine. Now, as far as the part which basically calls this coroutine, first we create a loop object. So we have this async io.get event loop. So what this does is it allows us to get event loop object. So if you remember from the lecture, I told you that with async IO, you need an event loop to manage things, right? So that's what you're doing here. So using async IO dot get event loop to actually get a loop object, and then this loop object will be used to manage the tasks. Now, what are the tasks? We basically create 3 tasks, and we use the create task function here. So we have loop.create task, and then we have countdown. So this is the first task. So we kind of have like this, you could say this list of objects which contains 3 um, tasks that we're going to be running concurrently. So we create a task for the first coroutine, then the second coroutine, and then the third coroutine. Now, how this makes the program different from the sequential one is that the program or Python now knows that, okay, these are tasks or coroutines that I can run concurrently. So what it can do is, as soon as, let's suppose, the first one goes to sleep, what it can do is it can initiate task B, and then as soon as task B goes to sleep, it can initiate task C as well. And then when one wakes up, it can kind of switch between these 3 tasks, right? So once we have these tasks, then we start the counter. So we say, okay, this is our start time, and then we say, okay, loop until complete. So we have loop dot run until complete, and then what we do is we use the async io dot wait tasks. Now let me go back to this table on the slide. So um, we're using this function here, or this method, right, which is basically you use the event loop dot run until complete. So what this method is basically uh, used for is to kind of run the set of tasks until they're complete. So the event loop basically kind of then runs until the tasks that you're passing it basically are completed. Now, what is this async io.wait? This function basically is also coroutine and can be used to switch tasks. So basically, we're kind of saying that okay, these are the tasks that you have, and you can kind of make these guys wait and stuff. So it takes a sequence, usually a list of tasks or futures, and we haven't really discussed futures in the lab yet, and then waits for them to complete their execution. So that's what we're doing here. Okay, now I'm going to run this. Now remember that the last sequential task basically took you um, 7 seconds to complete. Okay, around 7 seconds to complete. Now let's see how much time it takes us to run these um, tasks asynchronously, and then see how much time it takes. So you can see that it took less than half the time, right? Um, and what you have here is you have the first task that was initiated or was completed was task 3, right? And even though this is the last one in the list, this one completes first, because you can see that even though it comes at the end, this has the smallest delay, so it will be completed first. And you see that task C is completed first uh, for n is equal to 3, and then um, after that task B is completed, because it obviously was supposed to take around 0 0.8 seconds. And then task A is completed after 1 second. Now go back to the original program and you can see that um, you have the A task completing and you're going in a sequence. So you complete those after 3 seconds. But with the concurrent program, what happens is uh, you initiate task A. So the first task A gets initiated, uh, but then the program now has the ability to say, okay, now this one's been initiated, but while it is kind of going to sleep or it's waiting up for something, it can kind of put it to sleep, and then it can start the next task. So it would basically first um, start with task A, right? Task A would, and then it would go to sleep, and then it would basically initiate task B, and it would go to sleep, and then it kind of starts task C, and then that also goes to sleep, but that's the first one to wake up. So if that's the first one to wake up, it kind of is kind of marked as complete. Now you can see that the time that you see here for task C for the first task C is slightly over 0.5 seconds. So this 0. Or 0.0099 seconds is the additional overhead that is kind of used to, or is consumed to kind of first of all create these concurrent tasks, and then it also kind of includes the time where the program goes in and goes in with task A first, and then that goes to sleep. So it starts task B, and then that goes to sleep. So it says, okay, while you're sleeping, um, it can then go ahead and execute task C. And task C obviously gets completed after 0.5 seconds. But this additional overhead is kind of the time that is consumed for for this part. So you kind of put task, so you start task A and B first, and then you kind of put them to sleep, and then task C comes third, but it kind of gets completed first. That's the advantage of using async IO. And then after 1 second, you can see that task A completes, and then it goes to task number 3, and then so on and so forth. So that's how this whole thing kind of works, right? And it kind of helps out with these things. Okay, so I hope this is clear. Are there any questions about this? Um, Right. So this is the first two examples. Now let me quickly take a look at the other two examples. So maybe so the good thing about these examples is that they're from the book, so you can basically follow the book along, and it kind of connects the theory with um, you know how the concepts that are being covered in the book and on the slide. So you basically see these descriptions of the functions that were on the slide. So I'm kind of sharing the book here. So this is chapter 10 of the book, right? Um, so let me kind of okay, I should not have clicked that. Let me just go back. Okay, so these slides that these coding examples that I'm giving you here, they basically come from chapter 10 of the book. Okay, but there are some examples that it kind of uses from um, chapter 9 as well. Um, and so I will give you those examples too. Um, So this is again chapter 10 example 2 .py. So this is the example that we just looked at and kind of shows you how these things are basically done. Um, so you basically convert this into count into a into this coroutine by using the async keyword, and then this is the part that I just showed you. So this is your kind of main program, or the part that kind of runs or calls the tasks. Um, okay. Um, Now, of course, one thing that I just mentioned, and this is something that I kind of need to do here. Now, what will happen is if you do not use the async IO dot sleep function, and you use the time dot sleep. Now, time dot sleep basically is a blocking function, right? And so a blocking function basically means is that uh, once you give control to that function will not give up control. So even though you may have the await or the await keyword in front of it, if it's a non-blocking function, it won't hand over control. Okay, and that's a problem because in Python, not all functions support async IO. Okay, um, and that basically can be an issue. Okay. So that's why we kind of switched from async, so from time.sleep to async io.sleep. In fact, let me give you a quick demo. What you can do is if you, so yeah, I've already done that. So kind of using time.sleep, and then let's see if it kind of, right now with async io.sleep, we ran for about 3 seconds. Let's see how much time this guy takes. Now you can see that, in fact, it doesn't really do anything. Let me just remove the await keyword because it was kind of working with that last time. So now, yeah, so now you can see that this guy basically kind of goes back to the sequential mode. Um, and it basically takes like 7 seconds. And in fact, what happened with the await keyword, if I kept the await keyword in place, the program really did something that I was not expecting it to do, right? So if I use the await with the time, I guess it looks like it just runs for a second and then it kind of stops or something, or maybe one of the tasks is run, but the other ones are not run, right? So it does not. So this is kind of an indication that this will not probably support things being run asynchronously. So I guess only one of your tasks is completed and the other ones are just not completed. And even the one that is completed, it doesn't really seem to do much stuff, right? So there's a conflict, right? And the reason for that is that this function, which is from the time uh, library, right? This doesn't really support async IO. So um, you have to kind of use async io.sleep, right? So this is one of the downsides of using async IO because it's new. Not all functions, not all methods in Python basically support async IO, and this is one of the disadvantages. But what is happening is that people are working on this part, um, and and they're looking to kind of add support for this. So because async IO was officially introduced or officially implemented as one of the official features of Python, so Python core developers have been working to produce coroutine versions of the most commonly used Python blocking functions. So people are working on this, right? So um, hopefully over time, this issue will become um, less of a problem. Okay. Uh, Now, before I share the code for example one and example two with you, um, what I'd like to do is to kind of do one more example. Now, this example basically is taken from chapter 9 of the book, right? So this is example one from chapter 9, right? And we're in chapter 10. So what that means is that if you want to read up on these examples, you can kind of go ahead and kind of go to chapter 9 and you'll find these uh, in there, right? Um, but these examples are also presented in chapter 10, so you can kind of look at it in chapter 10 as well. So if we go back to chapter 10, um, and we look at this example, um, which is this is chapter 9 example 1. And again, let me show you one more thing. You can also find these examples in the repo or the GitHub repo for that is associated with the book. So if you actually go to chapter 9, you can actually find this example there. So you open this example, um, and this is the example that you see in the book right there, right? So this is chapter 9, example 1, and then on the same path, you'll find example 2 for chapter 9, um, which I already have open, I guess. It's this part. Um, and you can see that you have an asynchronous and a synchronous version for calculating prime numbers. Okay. Um, so you can kind of, I mean, I'll probably share the code with you, but if you already have the book's code, you can get the code from there as well. But I will share with you in a second. So let's just discuss example one now. So let me put it in Spider, and then I'll show you what this example does. Okay. All right. So this is, first of all, this is a sequential example to a numerical problem. And the problem that we have is we basically want to write down a function which evaluates whether a number that we pass to it, whether it's a prime number or not. Now, a number that is a prime number is typically a number that is um, not divisible by any number other than itself, right? Um, and so 0 and 1 are considered not prime numbers, uh, and 2 is considered a prime number. And then every number beyond 2 is considered a prime number if it is not divisible by any numbers smaller than itself, right? So this is just the property of the prime numbers. And so what we do is we kind of introduce 0, 1, and 2 as special cases. So we say if it's less than 2, so what that means is the number is, if it's 0 or 1, you would say that it's not a prime number. If it's equal to 2, you say it's a prime number because that's kind of like a special case. And then if it's kind of larger than that, you say, all right, If let's suppose it's divisible by 2, if the number is divisible by 2, you say, well, again, that's not a prime number. And then after that, if it's still not, if it's not divisible by 2 and it's a number which is large, what you do is you basically kind of go up to the square root of that number plus 1, um, and that, that's an integer number, so you force it to be an integer. So whatever the square root is, you basically convert that into an integer. So the decimal part is discarded, you add 1 to it, then you basically start from 3 and you go up to the limit um, in jumps of 2, and then you use this loop index. So all values in the loop index basically are kind of, you go through them and then you check if the number is divisible on those values, right? And if on any one of these numbers, uh, any one of these loop indices, if you get um, a remainder of 0, um, you kind of say that the number is not a prime number, right? Because you found something that was able to divide the number. But if that's not the case and you get to the limit, then you basically print that, okay, the number that you're looking at basically is a prime. Now, the problem with this function is that if you get very large numbers, so if you take this number, right, um, and you're basically looping through this, what will happen is that you have to kind of go to a very large value, right? For a smaller number like 157, the loop does not really have to run for very long. Uh, but if you have a really large number, then you have to really loop for a long time, right? Um, so let's first run this. Again, this program is sequential. So let's run this and then see what kind of happens, right? Um, okay. All right, so it gave me some warnings or whatever, but it was kind of able to run. I don't know what these were. I didn't have these last time I ran this. Let me clear the screen first and then maybe run this. Okay, I think my keyboard uh, seems to be out of batteries. It's not doing anything. Just give me 1 second, guys. I think I need to switch out the batteries for my wireless keyboard. Oh no, it's back on. I don't know why it does that, but it does that sometimes. Okay, so let me just clear this and run the function, run the program one more time. So let's run this and then see what it does. Okay, now it's not giving me those warnings or errors. So these are some of the issues that you have with async.io. I mean, or these threading libraries. I mean, they do stuff sometimes, and then another time they don't do that stuff. So again, I think one of the uh, I think one of the things that you can do is to maybe upgrade to the latest version of Python, because if you're because this guy was kind of introduced in Python 3.7. So if you have like a relatively early version of 5.3.7.2, I think, or 3.7.4, that's the version that I have. Um, you may get these sort of problems, but if you go like Python 3.8 or something, or the late version of 3.7, you may not have these problems. Okay, so what happened here? So um, when I actually run, when I call the prime function first time, you can see that there's a long wait as compared to the other one. So as soon as the first one is complete, the second one actually gets completed relatively quickly, and then the third one takes no time at all. So let me run this and watch the delay that will be kind of introduced. See, I'm processing. It takes like 2 or 3 seconds, maybe even more. And you're kind of getting that impression, if this was a long number, you may get the impression that the program is stuck. The program is actually not stuck. What is kind of happening here is that your program is actually taking time to kind of evaluate this prime number. Now, what you could have done here is, uh, if you had other tasks, which kind of were, like the second one basically takes less time or should take less time than the first one. What you can do is temporarily switch to the next task, and then temporarily take switch to the next task, um, and even though the longer task is kind of executing, you kind of put that on hold for a second and you execute a smaller or a task that would take a little bit smaller amount of time to execute. You basically put that in there temporarily. So what you do is, let's suppose you start with the first one, which has the larger prime number. Now that will take some time to complete. So what you do is you basically, what you could do is you could go into this ace prime function, and you could kind of put this to sleep for a second. And again, we'll basically use the async IO dot sleep 0. And if we do that, what will happen is we'll put temporarily, what we'll do is we'll take control away from the first one. We'll give it to the second one. And if that one also takes time, what we could do is put that to sleep for a second and then move to the next one. Now the next one will get completed really quickly because it doesn't take any time at all. And then once that is done, we can go back to wake up one of these two tasks, complete that, and that's how we proceed. Um, so we're kind of making this task asynchronous, although this task is not a very sequential task, right? And if you remember last time we were talking about, I guess in the slides we do mention tasks that are um, inherently blocking tasks, right? So this is basically that inherently blocking task. This is inherently blocking because uh, this task is inherently a sequential task. You really can't do anything about this. I mean, it's going to introduce a delay because this loop has to run and it has to run in a sequence. If you were to kind of try to make this loop asynchronous, there's just too many runs of this loop that you have to kind of do. Um, and so this is kind of like, so this is a numerical task, and this is kind of like uh, what you could say is an inherently blocking task. So making something like this asynchronous is not going to be easy, right? Um, so this is prime basically is kind of like it contains a blocking task. So um, I mean, it's not really going to sleep for some time. The delay is introduced because it's doing something during that time, right? Um, but what you could do is basically use that, uh, switch to another task which might be a little bit quicker, and do that first and then come back to this one. And what will happen is that your user will get the impression that the program is doing something, right? But actually, you're just kind of introducing a small task and completing that first, right? Um, and so this type of approach could be useful in maybe if you have some sort of a GUI or something that you're working with, where um, you know there's a task that is going to take a long time, and so what you could do is maybe temporarily squeeze in something else which doesn't take that much time and kind of execute that first, and then another thing first, and then so the user kind of gets the impression that the program is still running, it's not really completing. So that could be one scenario that I can think of. Now let's look at the um, asynchronous version of this. So I'll quickly put that here, and then I'll show you how that works. Okay, so this is example 2, again, chapter 9, right? Um, and what we do here is, again, so first we introduce async IO. The second thing we do is we basically introduce this async. So we make this function a coroutine. So we have to write the async keyword here. Now in this function, Um, what we do is, if a task has gone on for too long, so if I gets to 100,000, and this is actually modular division. So if you get to 100,001, or let's suppose you get to 200,001, so you've done like 200,000 iterations. What you will do is you will basically write this await async io dot sleep zero. Now sleep zero, as far as the delay is concerned, doesn't really do anything. But what the sleep zero does is that it basically um, kind of forces the coroutine to hand over control to the next coroutine, right? So if the next coroutine kind of comes along, and that next coroutine basically takes a smaller amount of time, um, you can run that, and let's suppose that coroutine maybe does not run for 100,000 um, iterations, so that will get completed first. And if it exceeds 100,000 iterations, what you could do is you will basically put it to sleep again, and you'll go to the next coroutine, and that's how um, you're kind of putting coroutines back to sleep. So the coroutines that run, or the consumers that run for a long time, you put them to sleep after a certain number of runs, and then you wake the next one. So you're kind of you're basically going in a circular fashion between um, uh, these coroutines, and in this way what you're trying to do is any coroutine that takes less time, you that should get executed first. So what I would expect is that in this case, uh, maybe this guy or this guy would probably get completed first, and you would expect that this one basically gets uh, completed at the very end. Okay. So we kind of introduced this part here. So this is new, and then we also introduce uh, we basically introduce the main function here, because we're kind of submitting these tasks through that. So we have task one, and again, this is using the loop event loop object, create task, and then you submit the first task, and then the second task, and the third task. You kind of submit these as three separate tasks, and then you basically write this as await async io dot wait, and you kind of, this is what we've done already. We did something similar in the previous example as well. So we have async io dot wait, and then we're submitting these three tasks. And then in our main program, what we do is we say, all right, we get an event loop, and then we run it until complete. Now, sometimes if you give it like a really long number, maybe it throws an exception, and if an exception is thrown, you'll catch this exception, and you'll maybe just print the exception, right? So people who kind of took the OOP2 course probably already know, they're just trying to handle an exception here. And then finally, at the end of this whole block, whether an exception is thrown or not, you will go in and you will close the loop. So let's run this. Now remember, in the sequential program, the task that was submitted first was completed, and then you went to the next task. And so they kind of executed or completed in order. Now I expect that this would not be the case here. So let's run this example and then see what happens. Okay, so you can see, so ignore this error because the program, I guess, did complete. Now look at this. So this one, the larger task was submitted first. The second task was submitted after this. Now notice that the second task basically completes first, right? This task basically gets completed first. Why? Because the program went to sleep after 100,000 iterations. So this first coroutine went back to sleep, right? And then the second coroutine basically is initiated in the meantime. And I guess it does not go up to 100,000 iterations. I guess the limit that you work out over here does not take you to 100,000 iterations. So the second one is initiated, and it is completed, right? And then when it's completed, you basically go to task number three. Task number three uh, also does not take a lot of time, so it also gets completed. And then you only have one task left, which is task one. So you kind of go back to it, and then that task basically gets completed. Okay. Um, Now, it throws this exception loop.close. So it says cannot close running event loop. I don't know. I generally have this problem when I'm trying to kind of do it. Um, I don't know, in my version of Python, whenever I call loop.close, I do get this error, but I really don't understand why this is happening. I mean, your kind of program is completing, so I don't I don't know why I get this. Okay. Um, so I guess now this is a good time where you can kind of run this code on your own. Um, let me quickly. Right, so you can see here in the books also mentioned await asyncio.sleep 0 command is used to facilitate task switching. So if you kind of introduce asyncio.sleep 0, what that does is it kind of switches the task. It will go to the next task. So this is kind of a way, so you can use this to put the current task to sleep and then go to a next task, right? So, you and if you remember, we looked at a little bit of parallel programming in Python, sorry, in Java. That over there we looked at these concepts of putting something to sleep or putting a thread to sleep. So that's what you're doing here. You're basically putting one um, task to sleep and then moving to the next one. Okay, and that basically is what happens here. So yeah, read the book as well when you get time because it kind of explains these things. We talk about inherently blocking. So now the thing over here is, of course, this is an inherently blocking task, um, and obviously navigating this is going to be a bit of a problem. So now what I'm going to do is I'm going to share this code with you, and then I'll look at the concurrent.futures as well, how to kind of introduce that here. So I haven't gone through those examples yet, so I'll try to go through those as well, and then um, once I'm through those, we have time left in the lab. I can discuss them in the lab, and if we don't have time, we can maybe quickly discuss these in the lecture. Okay. So that we'll do after that. But in the meantime, I think what you can do is maybe play around with the code that I've just discussed. I think a good exercise would be to kind of start off with a sequential task and then try to kind of convert it into an asynchronous task and then see how that goes. Okay, so try to do that yourself. So I'm going to share the code. So let me just create a directory here on Blackboard in the content folder. So let me create the content folder for lab 4 async IO, and let me just put the code in there. Okay, let's just edit this. Um, okay, please make sure that when you're kind of downloading the files, example1.py, so this will be for chapter 1, and then there'll be example1.py for chapter 9 as well. So when you're actually copying them, don't overwrite them, maybe give them different names. Just remember this, right? Um, So all I'm saying is when you're actually copying these files or you're downloading them, the names of the files, the way that the course is organized. So you'll have example1.py, but that will be for chapter 1, chapter 10, and then so this file right now, example1 from chapter 10. If you look at the Python file, um, it's called example1.py. Now I will upload another file for chapter 9, which is basically this one. So this is also example1.py. So all I'm saying is when you're kind of downloading these files, maybe you want to rename this as example1 underscore chapter 9 or something. Okay. Um, so you don't overwrite these files. That's all I'm saying. Okay. And you don't have to download these from here. You can also go to the GitHub of the page, GitHub page of the. Uh, so let me see if I have that here. There's a GitHub page for the book as well. You can basically go there and can download it from there. So if you go here, so code download. In fact, if you have the book, so this is the GitHub for the book, right? So you can basically download the code from here as well. So this basically contains the code for the entire book. So let me put that here. I'm putting that here. Uh, and you can download the code here from here as well if you want to. You can download the code for the entire kind of um, um, entire book as well. So maybe just download that directory, just like I've done. But put this here so you can kind of look at this part over here. Okay, so these are the scripts that we'll be using for this lab right now. I look at some other scripts as well, and maybe I'll introduce those, and then you can work on those later in your own time. But so yeah, so I guess you have enough to kind of play around with for now, and then I'll maybe share some more material in a little bit after I've had a chance to go through those myself. Okay.